everyone, welcome to part 4 of chapter 11. This will be our last section on chapter 11 on solids, liquids, and intermolecular forces. Today we are going to talk about phase diagrams. So phase diagrams display the state of a substance at various pressures and temperatures and the places where equilibria exist between the phases. So we talked about this equilibrium when we were talking about the vapor pressure, right? The vapor pressure at a given temperature. And we talked about the boiling point was when the vapor pressure of the liquid equaled the external pressure. So similar, we're going to talk about different equilibrium, not just now about boiling point, but about all kinds of them. So this is what a typical phase diagram would look like. We have our solid on the left. We have our liquid kind of in the top right, and then our gas more in the bottom right. We've got the line between solid and liquid. So from A to D, that would be our melting freezing line. And then from A to B, that's our vaporization or condensation, right? Like our boiling point, that's that line. And then we have C to A is going from solid to a gas. So that's sublimation and deposition, which we've talked a little bit about so far. We have some new things on this on these phase diagrams, though. We have the triple point and we have the critical point, both of which we will get to a little bit later in the lecture. So first part we're going to talk about is this AB line. So the AB line is the liquid vapor interface. It starts at the triple point, which is here, and ends up at the critical point, which is up there. So we're talking about the region kind of in between. The triple point is the point at which all three states are in equilibrium. So at this particular pressure and temperature, it is possible to have solid, liquid, and gas all simultaneously, which is really cool. I'm going to try and find a video and post it so that you can see what the triple point looks like. But again, it's a very specific pressure and temperature where all three of these states of matter can exist at once, which is super cool. So, but along this AB line, right, this is the boiling point. So at a given pressure, right, so we have pressure up along the left, at a given pressure, we have different temperatures of boiling points, which we've talked about back in the second lecture of this, of chapter 11. So, yeah, increasing pressure, right, will cause these molecules to be condensed, which makes the molecular arrangement closer. So we need higher and higher temperatures to cause them to boil. So we end this, boiling point line up at the critical point, which is B, which is another new thing for today. And above this point, this particular temperature and pressure, the liquid and vapor phase are indistinguishable from each other, which means you can't tell the difference between the liquid and the gas, which is kind of cool. So we have this critical point, like I said, so the critical point will tell you the highest pressure that you can have a liquid and the highest temperature that you can have a liquid or a gas, right? And then above this, like kind of in this region up here, this is where we will have a supercritical fluid. So the critical point, we have two things that make up the critical point. One of them is the temperature required to produce a supercritical fluid, and this will be called the critical temperature. Okay, and then the pressure that's also associated with this critical point is called the critical pressure. And at the critical temperature or higher temperatures, the gas cannot be condensed to a liquid, no matter how high the pressure gets. So you can keep ramping the pressure up, trying to, squish those molecules closer together. But at that critical temperature or higher, that gas can't be condensed to a liquid. Doesn't matter how much pressure you have on it. Okay, and so as we have the vapor being heated, and we have a sealed container, as we're having it heated, more and more vapor starts to be produced, right? The liquid starts to evaporate, more of it's going into the vapor phase, and as more of it goes into the vapor phase, the pressure inside that container starts to rise. Okay, And so that would be increasing our vapor pressure, right, which we've talked about earlier. So as we are increasing the vapor pressure, right, we're increasing the amount of molecules that are in the vapor phase, then we are increasing the density of that vapor, right? Simply because there's more vapor molecules in that space. So we're going and increasing the density of our vapor. So as we increase the density of our vapor, though, we are decreasing the density of our liquid, simply because some of those liquid molecules have now gone into the vapor phase, right? So if the density of the vapor increases, makes sense, the density of the liquid is decreasing. And this process keeps going, right? We keep heating it. More of the liquid molecules are going into the vapor phase. The vapor is getting more dense, the liquid is getting less dense, and at some point, this meniscus, right, this line that had been happening between the gas and the liquid phase starts to disappear. And the states start to commingle into one phase, and it's a phase that has the properties of both a gas and a liquid. It's called a supercritical fluid, which is really cool. So again, this is at extremely high temperatures and extremely high pressures. This supercritical fluid, it's not a gas, it's not a liquid, it's got properties of both. But again, we can't tell the difference between the liquid and the gas at this point. It's kind of a different phase of matter, supercritical fluid, which is cool. So that's, again, up above this critical point. The AD line is the melting point at a given pressure, right? So, as we increase our pressure, we are increasing our melting point, just following along, right? So if we have, higher pressure here, we've got a higher melting point than we would at, this particular pressure. So you can find the melting point at any particular pressure by just following along on that line. So below the triple point, so that's the point where I said that, solid and liquid and gas can all exist in equilibrium, which I think is super cool. But below that, the substance cannot exist in the liquid state. Okay, so below, at pressures below this triple point and at temperatures below this triple point, we cannot have a liquid. You can have solid or you can have gas, but you can't have liquid. And along that AC line, solid and gas phases are in equilibrium, so you can find the sublimation point, the point at which your solid will go directly to a gas, skipping that liquid phase altogether. And carbon dioxide is one that we're familiar with for sublimation, where it goes directly from a solid to a gas, and we'll look at what that looks like on a graph shortly, but it's crossing this line. So just in general, phase diagrams, we pretty much always have our solid over there on the left. We've got our liquid, like I said, kind of in the middle or, middle top, and then we've got the gas usually along the bottom right. So this is our vapor pressure curve that we were talking about in some previous lectures. So along that curve, you can figure out, what the pressure is, and you can follow the pressure across and find the temperature at which your substance will boil. Your substance will go from the liquid to the gas phase. That curve is the fusion curve. So again, along there, you can figure out at any pressure what the temperature is at which your substance will melt or, freeze, depending on which way you're going. Down at the bottom, we have the sublimation curve. So we can figure out at a given pressure what temperature your stuff will sublime. Will it go directly from a solid to a gas? Or like I said, if you're cooling it down from a gas to a solid. The critical point is right here where this line ends, that vapor pressure curve line ends, and above that pressure and temperature, we cannot have a liquid or a gas. We will have a supercritical fluid. And then the triple point, the intersection here, that is where all three of our phases, solid, liquid, and gas, can all exist in equilibrium, which, like I said, I think is pretty snazzy. So at 1 atm, so if we follow that across, we can figure out the normal boiling point, the normal melting point, and things like that. Because again, whenever we say the term normal, we're assuming that we're at 1 atm or 760 torr, right? So the normal melting point we would follow this line to 1 atm, and then we would go straight down to find the melting point. And then if we wanted to find the boiling point, we would go here at 1 atm and go straight down. So there you go, normal melting point, normal boiling point. Here's our phase diagram for water. Looks very much the same. We've got our fusion curve, we have our vaporization curve, our critical point, our triple point, our sublimation curve. So if we look, 760 torr falls above the triple point, which is why we don't typically see water sublime, right? Because we would have to do it at pressures that are lower than 1 atm. And we typically aren't working at pressures lower than that. So at 1 atm, we will see, our solid melt and our liquid boil. But very rarely would we see, would we see it go from a solid to a gas unless we were really able to drop the pressure a lot. So here's just another graph about the phase diagram for water, very similar to the last slide. I want to point out that water has a really high critical temperature and critical pressure, 218 atms and 374 degrees Celsius. So 374 degrees Celsius is high. It's not like super high, but 218 atmospheres, that's really high. And so the reason that water has such high critical temperatures and critical pressures are because of the strong intermolecular forces between the water molecules. Water is being held in the liquid phase by really strong hydrogen bonds. And so it already takes, quite a decently high temperature, right, 100 degrees Celsius, to turn the water into the vapor phase. Because, like I said, those really strong intermolecular forces. So we would need even higher temperatures, need even higher pressures to cause this to become a supercritical fluid because it has such strong intermolecular forces. Substances that have weaker intermolecular forces will have lower critical temperatures and lower critical pressures. Just one more little thing about water. This is kind of a minute detail, but the slope of this solid liquid line is negative. So it's sloped, it's sloped this way instead of this way, essentially. And that's a little bit unusual. And what that means is that as the pressure is increased at temperatures below the melting point, so like, here. So that would be, so here's our normal melting point, right, at 0 degrees Celsius. And so this would be at a temperature below, we can think about here, at a temperature below 0 degrees Celsius. And as we increase the pressure at this particular temperature, right, below 0 degrees Celsius, we can actually change it from a solid to a liquid, which is cool. So just by increasing the pressure, not changing the temperature, we can cause the solid to melt into a liquid at temperatures below 0 degrees Celsius. So this phase diagram, these are cool. You can manipulate them, right, by changing temperatures, changing pressures. So we're not always working with melting and boiling points at 0 and 100, right? We can also vary the pressures rather than varying the temperatures. Here is the phase diagram for carbon dioxide. Here we have the positive, right? Like instead of our solid liquid slope being negative, here it's positive, right? Because we don't have as strong intermolecular forces there. But if we look, the critical point up here is much lower than it was for water. 31 degrees Celsius and 72.9 atm. So that is much lower than what we saw for water, but again, it's because carbon dioxide, right? Carbon dioxide is a nonpolar molecule. So carbon dioxide is held together by London dispersion forces, which are fairly weak. And because it's weaker intermolecular forces, we have a lower critical point, we have a lower triple point, we have lower kind of everything. And if we look, so at 1 atm, at 1 atm, we have, right, this would be our normal anything. At this particular pressure, right, at atmospheric pressure, we don't have any kind of melting that can happen, right? We never cross this solid liquid line. We only cross this, solid this doesn't say gas over here, but solid gas line. So that's why we will see that carbon dioxide goes directly from the solid phase to the gas phase without ever hitting the liquid phase, because atmospheric pressure is below the triple point for carbon dioxide. Oh, there you go. So carbon dioxide can't exist in the liquid state at pressures below 5.11 atmospheres, which is, 5 times atmospheric pressure. So if we increase the pressure a lot, we can see carbon dioxide melt. But again, at atmospheric pressure, 1 atm, we will only see carbon dioxide sublime. We will only see it go from the solid phase to the gas phase, or the other way. So, like I was talking about before, this is our critical point for carbon dioxide. And since carbon dioxide, because it has, fairly low critical temperature and critical pressure, you can actually use supercritical carbon dioxide. So the point, again, supercritical fluids have some properties of liquids and some properties of gases. And we can use supercritical carbon dioxide as a solvent for extracting nonpolar substances such as caffeine. So this would be something that you would maybe use in like your organic chemistry classes, which is kind of cool. So again, a solvent usually implies a liquid, but here, a solvent could be a supercritical fluid. So let's look at how to read this. Okay, so it says, consider the phase diagram for carbon dioxide shown. What phases are present at each of the following conditions? So at 20 degrees Celsius and 72.9 atms. So we have 20 degrees Celsius and 72.9 atms. That looks like here-ish, right? And there, that puts us firmly in the liquid phase. Okay. Negative 56.7 and 5.1 atmospheres. That lands us right on the triple point. So here we would have solid, liquid, and gas, all three. That's why it's called the triple point. At 10 degrees Celsius and 1 atm, so 10 degrees Celsius, 1 atm, that puts us, here-ish, maybe a little bit farther to the right. That puts us firmly in the gas phase. Negative 78.5 and 1 atm, that puts us right along that sublimation line. So here, because it's going to be in equilibrium, we would have both solid and gas phases. And then 50 degrees Celsius and 80 atms is going to put us, here somewhere, right? So that's going to be above the critical point. So that would be a supercritical fluid. And that's it for today. That is how you read, these phase diagrams. And again, you can get lots of useful information from these phase diagrams. They're pretty cool. So again, if you have any questions, always feel free to send me them. Otherwise, we are done with chapter 11 and moving on to the last chapter of the class. See you all next time.